All right, so we're back with a couple of examples now. Here we're supposed to estimate the input value of the inflection point and then indicate the input intervals over which each of the following types of behavior occurs: increasing, decreasing, concave up, and concave down. All right, so remember the inflection points where it changes from one direction to the other. So from concave up to concave down, and that one has the same thing. So basically where that is. So, the best guess might be here, and so I would say that. And if we look, I would say that's probably 5. That might be 4. That might be 3, maybe. And again, getting these off of a graph is very hard to do. Even on your calculator, especially when you have a bigger spread, not just 0 to 10. Maybe it's 0 to 500, and you have to try to figure that out on a calculator. It's pretty hard. And so I'll show you a trick on how to do it. And right now we don't have to understand why it works, but we'll figure that out later in the class. So input value of the inflection point, that's going to be that x, well, let's call it approximately, because I'm not sure. It might be 3.2. I'm not really sure on that one. Now indicate the input intervals where each of the following types of behavior occurs. Well, it's increasing. Okay, well, where's it increasing? Well, guess what? It's increasing over the whole interval. So increasing, okay. And then decreasing, well, it's not decreasing at all, so we don't even have to worry about that. Concave up, well, it's concave up basically for x less than 3. And then concave down, we'll put over here, for x greater than 3. So then it's concave down here. All right, so this one kind of shows similar thing, except we're at a different spot. And so here, I'd say it's going to be, somewhere in that vicinity. What does that equal? I don't know. It could, I don't know. Maybe it's, if that's 1, 2, 3, 4, maybe it's at x equals 2, maybe. I don't know. So we'll say x is approximately 2. And again, these are really kind of not that, we can't really decide off a graph very easily. So that's the key to remember that. You want to get as close as possible, but estimating it sometimes can be very hard. So again, it's increasing over the whole interval. Now it's concave up from basically less than 2. So x less than 2 is concave up, and x greater than 2 is concave down. Okay, and so that's how these work. And again, there's other kinds examples in the book. They have some that are going decreasing, and then you have to figure out where it is. But what all it boils down is to picking that inflection point, and then just kind of saying, okay, well, that's up, that's concave down. And if it had gone the other way, say like this, then your inflection point, it would have been concave down up to that point, then concave up afterwards. So it really doesn't matter which way they are. You just have to kind of decide what they are and if it's increasing or decreasing. All right, so part A says discuss the scatter plot suggested change in concavity, and then what types of functions might be appropriate to model the data represented by the scatter plot, linear, exponential, logarithmic, logistic, or quadratic. Now note in the book, they leave out this one. And so we really need to put that in since this is a logistic section. And so what do we see here on the first one? Well, does it change concavity? Well, no, it looks like it's all just concave down. So we can say no. What about this one? Well, that one looks all concave up. So no. Well, that one looks pretty linear. So I'm going to say no there without doing anything. And this one, I would say no as well. So none of those really have any concavity going up or down. Now, if you did see it, you're going to see something like this. It's going to come down, and then it's going to go over, and that's the one where it looks like a 2. Or if we have the increase one, it kind of comes up and then it goes over that way. Then that's the changing concavity there. Okay, so those are the differences. So what about this one? What could we say? What kind of a function would model that? Well, I think it could be, a log would keep going up, and if that keeps going up, that would fit a log plot. So I would say a log. And it also could be a quadratic because now it could come down over here. So I'd say a log and a quadratic. Those would be the two I would think on that one. Okay. What about the next one? Well, the next one, that one looks like it's pretty much just continues going up and it's the shape. So I would say this one probably is going to be an exponential, most likely, but could it be quadratic? Because it could have come down here and then it could have came up on that other side. So quadratic could also be the case. Now this one, that looks just pretty linear to me. So I would say, well, we got our first linear function here. Now this one, it's decreasing. So, we could have the exponential because it could just come and never get to that zero. We could have logarithmic if it keeps coming down and then it goes below zero. Or we could have it come down and then go back up, and so it would be quadratic. So we could have a log, we could have the exponential, and we could have the quadratic, I think, on that one. So that's kind of how I would look at those and see, which shapes and things like that. And again, if you saw something like this, immediately you'd say, oh, it's logistic, and we would be done and we wouldn't even have to worry about looking at any of the others. But those are kind of practice for previous sections. All right, so here we're supposed to identify the logistic function as increasing or decreasing, and then we're supposed to use limit notation to express the end behavior of the function, and then write equations for the two horizontal asymptotes. All right, so what about this first one here? Is it increasing or decreasing? Well, first off, we have to look at our b, and we have a 2.4. So it's b is greater than a 0. And so if it's greater than 0, remember, we go over here, greater than 0, it's increasing. Okay, and less than 0, it's decreasing. So we can say this one is increasing. Okay, and so let's look at this one while we're doing it. Let's kind of side by side. Well, that's a negative, so that one must be decreasing. Okay. All right, what about the next one? Use limit notation to express the end behavior of the function. Well, if it's increasing, that means we have something like that. And if this one's decreasing, we have something like that. So we can say on this one, the limit, and let's just call it of s of t as x goes to negative infinity. Well, as it goes to negative infinity, that's going to be 0. And the limit of s of t as x goes to positive infinity, well, that's going to go to this value here, 10.2. Okay, and so that would be what we get on that one. Now, on this one, what do we get for our limits? Well, limit of g of x equals, and the limit of g of x. And here if we go, x goes to negative infinity, x goes to positive infinity. All right, so going to negative infinity, we're going this way. Well, that's going to go to 95. Oops, 5, not 2. So we'll go to 9. Okay, it wants to be a 5, or 2, not a 5. We'll make it a big 5. All right, so it goes to 95. And then what about this one? Well, that one's going to go to 0. Okay. And so write equations for the two asymptotes. Well, our asymptotes are going to be y equals here 10.2 and y equals 0. And here it's going to be y equals 95 and y equals 0. Okay, so pretty easy after you get to know what we're looking at. You know that L is going to be one of the asymptotes and then 0 should be the other. And so you have 10.2 and 95. So that's what I would do for this one. And so I think we've answered all those questions. So let's go and we'll pause here and we'll come back with some more.